Hello, this is Geoffrey Frankel with Solutions in Chemistry. Today I'm going to talk about calculations with acids and bases in IB Chemistry HL Paper 1. We need to understand the relationship between Ka and pKa and hydrogen ion concentration and therefore pH. Let's take the standard equation, which is Hx goes to H plus X minus for an acid. In the case of a strong acid, completely dissociated, Ka. In the case of a weak acid, there's usually more Hx than is H plus this one, X minus. Weak acids have a range of strength, and we're going to compare that with now let's look at the K value, which is that equals the concentration. If you convert that to a pKa, you get a pKa of 3 over. This is the smallest pKa, and therefore A is the answer. Weak acid. Go through that again. And a strong acid. Ka equals 1 times 10 to the minus. Let's look at the Ka. Ka low for a weak acid, log high for a strong acid. Therefore that equals, look at the concentration of H plus. It's low for a weak acid, high for a strong acid. Let's look at the pH. Therefore this pKa is smaller, equals minus, therefore that indicates that H plus is stronger. And because of the negative, these get reversed. For a weak acid, it's high, and for a strong acid, it's low. Now these are relative figures because high means something like pH equals 3, 4, 5, 6. Low means pH equals 0, 1, 2. There. Depending on the concentration of the strong acid, and depending on the concentration and the Ka value for the weak acid. And let's go to pKa, and that equals minus log Ka. And so just as this was reversed, that will be reversed. So it's high for this and low at this level. And these figures high and low will depend on the actual Ka values. I have described a strong acid as one that is completely dissociated and a weak acid as one that is not completely dissociated. However, this table can compare a weak acid and another weak acid which is stronger. There are two ways of looking at this table. Either you have a weak acid which is not completely dissociated and a strong acid which is completely dissociated. Or the other way of looking at the table is you have two weak acids. This is the stronger of the two. And so these lows and highs and lows are relative. Given this table, we're now looking at which acid is the strongest. If we're looking at, as they give us pKa, looking at pKa, we want a low pKa. So we can immediately say acid A is stronger than acid C. In terms of Ka, we're looking for a strong acid, so we're looking for a high. So the highest of these two is B. The only two we need to compare is A, which has a pKa of 2, and B, which has a Ka 1 times 10 to the minus 3. We then either anti-log that or we log that. If you anti-log that, that comes to the Ka for it is 1 times 10 to the minus 2. If you log that, the pKa equals 3. What are we looking for? We are looking for a pKa of the lowest, which is that one, because the pKa is 2 compared to pKa of 3. Or we're looking for a Ka of the highest. If you compare that Ka with that Ka, clearly that Ka is the highest. So the strongest acid is A. Now it's taken me a long time to describe this thought, but maybe you can remember this pattern or you can quickly work out the pattern using this argument. Now, if I've mentioned this before, if you're having a difficulty with this argument, it's because you're having difficulty with logs and exponentials. And the answer is, as I've said before, find a mathematics textbook, find the chapter on logarithms and exponentials, and work your way through it. 10 minutes a day for a month until this becomes easy for you. Because in principle, it is easy. It's worth 1 mark in paper 1, and if they don't give it in paper 1, there will be a question in paper 2, and it could be worth 3, 5, 8 marks. Learn how to do this question. Based on the equation that we're going to use for these, hx goes to h plus x minus, and Ka equals concentration of H plus times concentration of X minus over the concentration of Hx. We now know that the weakest acid is the one with the smallest concentration of hydrogen ions, and therefore the smallest Ka. And what is the smallest Ka? That one. You can do this in less than 10 seconds. From the previous questions, we know that a strong acid has a high concentration of H+, it has a high Ka, it has a low pH, and it has a low pKa. So even when we're looking at a group of weak acids, we can say that the strongest of these weak acids will have a low pKa. And that is that one. So if you remember this simple pattern, strong acid, high concentration of hydrogen ions, high Ka, low pH, low pKa, this becomes possible to do in less than 10 seconds. Another one that you should be able to do in less than 10 seconds. What is the relationship between Ka and pKa? It is that pKa equals minus log Ka. And if they asked you what is the relationship between concentration of hydrogen ion and pH, you would say pH equals minus the log of the concentration of hydrogen ion. So these kind of questions, they only take 10 seconds. Make sure you know them so that you can do them in the 10 seconds. From what we saw before, if a pH is low, a low pH, then you have a high concentration of H+, and you have a high Ka. The lowest pH will have the highest Ka. So what is the highest or the greatest Ka? There it is, 6.8. Again, another question that takes less than 10 seconds. In this question, they've mixed Kas and pKas. We know that the strongest acid has a high Ka and a low pKa. So we look first for the high Ka, which is this one. The 1 times 10 to the minus 4 is higher or greater than 1 times 10 to the minus 5. And we look for the lowest pKa, which is easy, that's 3. So the question is, which is the strongest, this one or that one? There are 2 ways of doing it. You either anti-log that, and you get 1 times 10 to the minus 3, and that's the new pKa. Or you log that, take the negative, because pKa equals minus log Ka. So that comes to 4. So you're looking for the lowest pKa, which is that one, or you're looking for the highest Ka. That one again. So the answer is B. This is another question that can take you 10, 15 seconds. The interesting thing about this question is they don't use the word buffer. Now, maybe buffer would help you, or maybe it wouldn't. I don't know. Principles are the same from what we've been dealing with. We start off with Ka equals H plus, this is for the acid, X minus over Hx. Due to the equation, which we've done before, which is hx goes to h plus x minus. In this, we have some data to put in, and we have to put it in quickly. We're looking for the acid dissociation constants. This is the thing we want to know, so they must be telling us all of that. So, what is let's take the simple ones. The simple one is the concentration of hx. They tell you concentration of hx is 0.1. In paper 1, they never mix units. You will find the units are always the same, so you don't have to worry about mixing them or changing them in any way. Use the units they give you. In addition, in paper 1, they don't expect complex calculations, so you'll find that, lo and behold, this is 0.1, this is 0.05. It's 2-to-1 ratio. It's a very simple ratio. You will find that within paper 1 questions. So let's go back to this. Concentration is hx there. The concentration of this, well, they give it to you, it's in this, which is going to be the same as that, 0.05. Now, what is the concentration of H+? Well, they tell you the pH equals 3. If the pH equals 3, you therefore know, because pH equals minus log H+, that the H+ must equal 1 times 10 to the minus 3. We put up here 10 to the minus 3. Lo and behold, this goes into that 2 times. Therefore, that equals 0.5 times 10 to the minus 3, which equals 5.0 times 10 to the minus 4. There you go. Now, this one would have taken you a little bit longer if you were writing it out. If you can do these kind of things in your head, it would be so much better. But even so, writing it out shouldn't take you more than 30 seconds or so. Because all you have to do is write this down, put these figures in. This is the concentration of the acid. This is the concentration of the salt, sodium salt. And this is the concentration of hydrogen ion. And the answer is B, 5 times 10 to the minus 4. This is another question where the word buffer is not included. And so you have to know which one is a buffer. Why am I saying buffer? The reason I'm saying buffer is because they're asking you, could you calculate a pKa? If it's a strong acid or a strong base or a salt, a neutral salt, then you don't have anything like a pKa. You only have a pKa when you're dealing with a weak acid. So you go through here, you can eliminate that. That's ridiculous. You can look at this one, and you can look at this one, and you can look at this one. So let's look at them one by one. You've got exactly the same molar quantities of sodium hydroxide solution and ethanoic acid. This cannot be a buffer. This is a sodium salt of ethanoic acid. This is the sodium salt of ethanoic acid. This would not be a buffer. This one, they have given you half the quantity of the acid as compared with the sodium hydroxide. So what you'd end up with is the sodium ethanoate and sodium hydroxide. This would have a pH of about 13 to 14. This is not something that would help you calculate any kind of pKa. So that leaves us the last one. We have twice as much ethanoic acid as sodium hydroxide of the same concentrations. Perfect for a buffer. That's a buffer solution. In another question, they might have said which of these would form a buffer solution, in which case you would say this one. So this one forms the buffer solution. Therefore, when you measure the pH of this, you can get the pKa of this acid. So this is the answer. Now that was a quite complicated one on the part of the examiners, but in principle it's still possible to work out. As soon as you see that there's a pKa talking about a weak acid, and if they're mixing acids and bases, then they're also probably talking about a buffer. So you need to look for what is the solution that would create a buffer. and it's this one. And you don't have to do any calculations. You just have to realize what is the solution that would create a buffer. This one, D. This one looks confusing when you look through it, but it's very simple. You start off with the hx goes to h plus x minus, and then you get the Ka. They tell you there's a Ka, so you write the Ka equation down. H plus x minus over the concentration of hx. Then all you do is you substitute with what you've got. Now they give you the Ka, 1.8 times 10 to the minus 5. H plus is the thing you're trying to determine, so you leave that there. X minus. They tell you the X minus has a concentration of 1.0. So put that in. They tell you the Hx has a concentration of 2.0. So therefore H plus, which is what you're looking for, equals 2 times 1.8 times 10 to the minus 5, 3.6 times 10 to the minus 5, which is B. A very simple calculation, which you can do in 10 seconds or so once you realize it's based on this simple equation. As soon as you see that, you must know that this must be the equation on which it's based. If you found this YouTube video helpful, please subscribe to my channel, Solutions in Chemistry, and look at my other videos. Thank you.